One thing that's really important to remember in really all of our algebra in this class is that when we have symbols like f and x and y and g and all of those things, they're just symbols that we choose to represent certain relationships, scenarios, maybe real-world values. But the fact that we pick things like x and f, it's all somewhat arbitrary. And there's no reason why, when we're talking about some function, we have to think of it as its own unique thing and that it has behaviors and properties that only possibly apply to it and nowhere else. And sometimes they kind of do, but really we can get those relationships in more complex and sometimes meaningful ways that if we don't want to just talk about putting in the value x, because we have some maybe context in which that's not quite enough, we can look at what's called the composition of functions, where when we put in the value, we put it in terms of some other function. So we got things like f, that little circle g, that's the composition of f with g, or f at g. That is the function f evaluated at the function g of x instead of just the single value there, x. That circle notation is sometimes attributed to the mathematician Bourbaki, but it's not actually of certain origin. And then similarly, we can talk about taking g at f, where that would be g of f of x, and importantly, these are not necessarily going to be the same. That is, g of f is not always f of g. It can be, and in one really important case that we'll see in 2.7, it is. But just understand that we're talking about maybe bringing an extra layer of complexity into a relationship. Now, this is a lot of notation, might not be super clear why it might matter, so let's take a quick real-world example. And let's say you go to the store and you're feeling hungry but don't want to get too much, so you're going to go buy some bananas.
I mean, it's one banana, Michael. What could it cost? $10?
You've never actually set foot in a supermarket, have you?
And when you're going to buy your bananas, you're thinking to yourself, man, these bananas seem really expensive. I'm going to bring a coupon with me. So you bring a coupon that will let you get them for $2 off. So what you're looking to spend on your bananas, that's $2 off per banana, because these are weird bananas, obviously, is Cx is equal to x minus 2. Because for every banana x, you're saving $2. Let's say you get to the store and you find out that the bananas themselves are on sale because the store realizes, why are we selling bananas for $10? That's ridiculous. So their sale price puts them at 20% off, which means they'll have the sale price of 1 minus 20% x, or 0.8x. So when you go and buy those bananas, you're not only going to get to use your coupon, you're also going to get to use the sale price. And that relationship, that connection, can be modeled by the composition C of S of x. That is, the cost the cost of the bananas with the coupon, also including the sale price of the bananas. Where this assumes that you're applying the coupon at the end. You could actually go in the other direction, get the sale first, and then the other way. I'm not going to worry as much about that, but for now, this would just be our function c, but instead of having a x in there, we have s of x in there, which means we're taking 0.8x minus 2. And so when we were talking about things like difference quotients, that was actually kind of an application of compositions. It's a special kind of composition with some other transformations thrown into it. And actually I should do the other direction as well, where, say instead you were to, I don't know, somehow apply the coupon before the sale. That would be looking at something like s of c of x, where that would be s at c of x, which, oh boy, that's bad with how I write my c's, but that's okay, we're going to live with it. You'd end up with there 0.8 times x minus 2, which means you would end up paying, in that case, 0.8x minus, do that math quickly in my head. I don't know why I'm doing 8/5. Just do nicer as a decimal, 1.6. So actually it'd be a slightly worse deal if you did it that way. But also this highlights the idea I have right there, that these are not necessarily the same. Anyway, that's a quick example. Let's get a couple more just with a more abstract context to see how this works in terms of general non-applied functions. So for this example, we want to take the functions f of x equals 3x squared minus x plus 10, g of x equals 1 minus 20x, and h of x equals 5, and evaluate a few different compositions here, where the first one I'm going to look at is f composed with h of x. It's a little bit small there, but that's okay. So in this case, what we're going to have is f evaluated at h of x, and that's going to just end up being our function 3x squared, but that's going to be a 5 there for x because we're evaluating at h, minus x, which here is instead of 5, plus 10, so you're going to end up with 75 minus 5 plus 10 equals 80. And so we can understand here that anytime we're talking about evaluating a function, if we want to be weird and picky about it, we could instead contextualize that as our main function being composed with a constant function. Meanwhile, for our second example, we're going to do something that has a little bit more involvement to it. We're going to take f composed with g of x, the composition you're most used to seeing probably. You want to pronounce that fog. That's not an O, it just looks like one. Anyway, here we're going to be taking f and evaluating that at g, where g is 1 minus 20x. So everywhere that we have an x in f, we're going to replace that with a 1 minus 20x instead. So instead of 3x squared, we'll have 1 minus 20x's squared. And instead of having an x, we'll have a 1 minus 20x. And instead of having a 10, well, there's no x's there, so it'll still just be a 10. But we can simplify this a little bit, where I'm going to condense the terms, skipping the half step of all the FOILing and all that. We'll end up with something like 1200x squared minus 100x plus 12. Where you should actually check to make sure that this is how it all works out, but you should get something like this. Meanwhile, if we went the other direction, g circle f of x, which I know you're going to have the inclination to call the goff or the goof of x if you prefer. If you remember it, that's fine, but just know that really what we're doing is taking g and evaluating it at f, which would end up being g of that, well, binomial, or excuse me, not binomial, quadratic. It's actually a trinomial. 3x squared minus x plus 10, which means that we are taking 1 minus 20 times 3x squared minus x plus 10, or multiplying this all out, simplifying just a little bit, negative 60x squareds plus 20x's minus 199, which very importantly is obviously and in many ways not equal to f composed with g. It's actually a very, very special case when we have that the composition goes in both directions. Like I said, we'll see that in 2.7. But before we finish here with 2.6, I'd like to do one more example talking about the domains of compositions.